is Dr. Hal Finkel. He's now the lead for compiler technology and programming languages at the Argonne Leadership Computing Facility. Hal?
Samir, can you hear me?
Yes, we can. Thank you.
Okay, great. Thank you very much. And thanks for the organizers for inviting me to speak today. I'm going to talk to you today about LLVM. I'm going to explain what LLVM is and why we're investing in it for Exascale, and share some of the recent work that we've done in this space. So let me go on from this. So first, let me start by explaining what LLVM is. So LLVM is an open source, liberally licensed infrastructure for creating compilers and other toolchain components, including just-in-time compilation engines, static compilers, and so on, in addition to various kinds of static analysis. The most sort of well-known component of LLVM is Clang, which is a modern C++ front end for LLVM. It is arguably the best C++ compiler available in terms of front-end technology. And what I'm going to talk about is the way that LLVM and Clang are going to play significant roles in our Exascale computing ecosystem. Okay, so one thing that's important to note, and I'll note as we go along, is ways in which LLVM is important both in industry and to our vendors, and also directly for our research programs. Okay, so what is LLVM? So first thing I'll note is that LLVM is not a low-level virtual machine, despite what you may have heard the acronym to stand for. LLVM is an infrastructure for creating compilers, and you can use it, of course, as part of a virtual machine, and some companies do that, but it itself is an infrastructure for creating all kinds of compilers and tools. And the core component of LLVM is this compilation infrastructure that is composed of several different stages. So LLVM has what's called an intermediate representation. It's essentially the language that's used to represent programs. And this intermediate representation is then put through various kinds of transformations using this modular infrastructure. And so there are architecture independent simplifications. There are architecture aware optimizations, such as auto-vectorization. There are various kinds of backends that can be used. So you can do things like type legalization, instruction selection, register allocation, all those things which are really dependent on a particular architecture and are tied to that architecture. And yet there are commonalities across different architectures. And so you can have a common infrastructure to support a lot of these code generation tasks, and LLVM has such an infrastructure in addition to a lot of specific code for various backends. And then once the code has been put through this process, then you can print it to assembly source code in files. You can generate binaries directly. You can compile it just in time, link it dynamically into your application, and execute it directly. All of these things are possible with LLVM. And I mentioned Clang. So Clang is this C++ front end. It supports modern C++. The developers of Clang are on the C++ standards committee, and new features in C++ are often implemented in Clang even before they're standardized for testing purposes. And there's a really large focus in the Clang's development practices on having good error messages, good warning messages, making C++ a kind of friendlier language to work with. And so the source code comes into Clang, it goes through parsing and semantic analysis and so on. And then two things can happen to it. So one is it can go through code generation, which means you generate LLVM-IR and run through the pipeline on the previous slide. Or you can use Clang's built-in static analysis engine, which has also been improved over time. It now has multi-translation unit capabilities. It has the ability to tie into the Z3 SMT solver to do very advanced proofs of various kinds of correctness properties. And so you can leverage all these different capabilities in Clang. Using Clang is generically pretty simple. It's a drop-in replacement for GCC and actually for MSVC on Windows. It has a scalable LTO to do link time optimization. And so you can apply a link time optimization over large code bases using the scalable LTO. That's a really important feature. All right, but as I mentioned, so these are two components in LLVM, and the LLVM project as a whole has many components. So here I've a screenshot of the sort of major components within LLVM. There's the LLVM core libraries themselves. Those are the things that are called LLVM, but that's the kind of key portion that I talked about on that first pipeline slide. Then there's Clang. There's LLDB, which is a debugger. There's libc++, which provides a C++ standard library implementation. There's an OpenMP runtime library. There's Poly, which is a polyhedral optimization project. There's LLD, which is a linker. And there's compiler RT. Now, compiler RT is a set of compiler runtime libraries. But the most important things, in some sense, that are in there, especially in our context, are the sanitizers. So these are instrumentation-based debugging tools that can be used in order to compile instrumented code that can detect things like buffer overruns and race conditions and all sorts of stuff like that, uses of uninitialized memory, and report that to the user. And in HPC, these are actually fairly important because oftentimes if you're trying to debug a problem at large scale, maybe your program is crashing, but it could take a long time to get to where the program crashes when you run it. And so you having a tool which has low overhead is really important to detecting problems. And these instrumentation-based debugging tools are very important because they specifically are designed to have low overhead relative to other such approaches. There are a couple of other new things which are in LLVM which are worth noting. One is Flang. So Flang started as a collaboration between the Department of Energy and NVIDIA, PGI. And ARM and other vendors are now also involved and have been for some time. It is a Fortran front end. So the idea is just like Clang has the ability to take in source code and convert it into LLVM-IR and then it can be compiled. Flang takes in Fortran code and converts it into LLVM. There actually are two different kinds of the collaboration has produced kind of two different artifacts, or is producing two different artifacts. One is there's a version of Flang that's based on PGI's kind of old Fortran front-end code base. And I say it's old, but I mean, it's been maintained, and this is capable of producing production quality code for CPUs, including OpenMP support, and it has some preliminary GPU support as well. And then there's also a part of the project was called F18, which produces a new modern front end written in modern C++ for Fortran. Parsing, semantic analysis, all these kinds of things. And this is now part of the LLVM project. So the LLVM project has Flang inside of it, and is being developed by a community that is putting code as it's being developed into that part of the LLVM project. And so eventually the LLVM project will have a production quality Fortran front end to go along with Clang and the other pieces of the project. But one thing that's useful to note is that Flang is not directly generating LLVM-IR. So Flang interfaces with another component that's now in the LLVM framework that is called MLIR. And this is a multi-level intermediate representation, which was originally developed as part of Google's TensorFlow project, but is now part of the LLVM project. And it's an IR that has an extensible set of dialects that can simultaneously coexist and can be lowered in an incremental way. So front ends such as Flang or TensorFlow can produce MLIR. MLIR has dialects, of course, for Fortran to support Flang and OpenMP and so on, but also linear algebra dialects, affine loop dialects, and so on that can be used for advanced loop transformations and other kinds of transformations. And so what happens here is that LLVM can generate, front ends can generate MLIR. Those get lowered through this pipeline, and then once they're done with this pipeline, they can go into the regular LLVM pipeline. But you can do higher level transformations at the MLIR level, and this is something that is being used for Flang. and for TensorFlow, and is being explored in the context of several other projects. But I mentioned that LLVM is, is already an important part of our Exascale ecosystem, and I just want to sort of visually indicate why. If you look at the ecosystem of vendors that provide our hardware for Exascale, they all use LLVM and contribute to LLVM. So they're all part of this overall community, and this is what makes this community such a strong and important community in the context of our Exascale development. And of course, we all take advantage of the fact that companies that are not really part of our Exascale ecosystem, in particular, companies like Apple or Google or Qualcomm or Sony or Facebook or whoever, they also are contributing a lot of resources to LLVM, to suit their own purposes. And so we all kind of contribute to this common ecosystem, and we benefit from the contributions of people outside of our immediate computing ecosystem. And we have important contributions, of course, also from the labs, from academia, and so on, in addition to the vendors. But this picture, I think, really explains why LLVM is such a central component in our compiler ecosystem for Exascale. So, to summarize the sort of state of things, LLVM is a strong, has a strong ecosystem with many contributors, and it has a well-defined intermediate representation, which is used by a number of different languages: Clang for C and C++, Flang for Fortran, but also languages such as Julia, Rust, Numba in Python, Swift, all of the major ML frameworks like TensorFlow has their XLA component for using LLVM, PyTorch has Glow, and so on. There are lots of different backends, and it allows for the efficient creation of different backends. And it has a state-of-the-art C++ frontend, which includes CUDA support. We'll talk more about that later. Scalable, linked optimization, sanitizers, and so on. And we have a strong community, which means we work hard to maintain a high-quality coding standards and the like. All right. So you can look at that vendor diagram I showed before, and you can compare it to what we are expecting in terms of upcoming Exascale systems, and you can see there's a strong overlap between those vendors and what we expect. And this collaboration is fairly strong, and we have conversations with these vendors both sort of in the openness part of the community, and of course also as part of our procurement processes. And this kind of close relationship is really, really important because because the labs have this investment and ECP has an investment in LLVM, we have people who are working on LLVM and working on the compilers across the laboratory complex. And this means that when we have conversations with the vendors, we can have conversations which in many cases are more like peer conversations as opposed to conversations where the vendors are simply telling us what they can do and we have to nod or frown. So I think that this is an important part of this relationship, which has really helped things going forward. All right, I'm going to talk about some features in LLVM and how we're adapting them. I'd like to start out by talking about this feature, which is now nearly a decade old, but it's a really great example of how the development process between HPC and the rest of the LLVM ecosystem can work very well. So we had a desire to implement warning messages for MPI functions, and so we were able to develop a feature in Clang, which we were able to generalize. So it's not specific to MPI, but we developed a general feature to add these special attributes that could be used in order to generate warning messages, such as the one you can see on the slide, for data type incompatibilities with MPI calls. And these tags are now inside the headers for MPitch and OpenMPI and so on. They can be used for other libraries like HDF5. And it's a generic mechanism. And this is a really good example of how the HPC community was able to contribute to this larger project in a way which specifically benefited the HPC community, but did so via the introduction of a more general feature that is now in wide use in many different places. All right. A feature which is sort of more specifically targeted at HPC is CUDA. So Clang can function as a CUDA compiler, and And this is something that I encourage people to try if they are interested. But the other thing I'll point out is that this capability of compiling CUDA code is something that was adapted by AMD in order to form the basis of their HIP programming model for their GPUs. And so, this capability, again, it started out as a kind of specific capability targeted at a particular architecture, but now has really seen a lot of generalization. And we're also seeing contributions from Intel and others to add SYCL support to Clang. So all of the sort of major single source programming model systems that can be used for programming GPUs are part of the LLVM community and part of Clang, and this is extremely important for our kind of overall strategy going forward. Okay, and part of the reason for this is that LLVM has backends that can support all of the GPUs that we expect to see at Exascale. So this is both GPUs from NVIDIA, from AMD, and also from Intel. The Intel GPUs go through a path that involves a SPIR-V translation layer because SPIR-V is used as their preferred intermediate representation to be fed to their backend compiler, IGC. But regardless, all these things can be converted from LLVM, and you can integrate all of these things into a common ecosystem. All right. I'm going to talk a little bit specifically about OpenMP support, as that's quite important for us. OpenMP, as you know, is a program model that allows you to add pragmas into your source code to express parallelism and now accelerator offloading. Now, for accelerator offloading, the pragmas are perhaps a bit more complicated than just for CPU offloading because you have to deal with data. But you also have to deal with different levels of parallelism, and and together this is a challenge, but it's extremely important for targeting accelerators. And Clang has OpenMP support. We'll talk a little bit more about that later. The OpenMP support is integrated into Clang and into LLVM, and it supports the creation of fat binaries. So it supports the ability to create binaries that will run on the host, but have embedded sections in them that have accelerator code for different architectures, and then can then run on those different architectures with the support of runtime library. So there's a host runtime library, libomp, that's part of the LLVM project for doing host parallelism. And there's also libomp target, which is the target offloading runtime for LLVM. And there are a variety of plugins for libomp target to support specific offloading targets and architectures. The OpenMP support in Clang has been the subject of a lot of investment, both by ECP and also by our vendors. And so you can see here that if you look at the, if you compare the support that recent versions of Clang have for OpenMP versus other compilers, especially for the NVIDIA architecture, which is the most mature, you can see that in the tests that we have run at Argonne, it's really on top in terms of overall support in C++. And there's even a project under ECP to develop OpenACC support in Clang and LLVM. And this is being led by Jill Denny at Oak Ridge. And it relies on a translation capability between OpenACC and OpenMP to take advantage of all that infrastructure that we've been developing. One thing that I really want to talk about now is the work we've been doing in Argonne in order to improve loop optimizations and also do optimization specifically on parallel programs. So loop optimizations first. So this is work that's led by Michael Cruz at Argonne. And one thing that you may be aware of is that most compilers provide some ability to have pragmas on loops to control various kinds of optimizations, whether it's vectorization or unrolling or unroll and jam or what have you. And so, but all these pragmas are pretty ad hoc. They don't compose particularly well, if at all. They have all sorts of odd restrictions and compatibility rules. And one of the things we started looking at was, we said, well, okay, if people are going to use these pragmas for tuning, and it's certainly preferable to handwriting out optimized code, then we really need to think carefully about the model. Make sure that we have pragmas that can be composed, that can be combined in various ways, and can really express the set of optimizations that people really want to perform. And so we started developing a set of these composable pragmas and an implementation of these to demonstrate that this would work effectively. And this is what we did. Now, of course, on the previous example, we had very simple. On the previous slide, we had simple examples. Here is a more complicated example. This is one way that you might use these pragmas in order to optimize a call to dgem. And here you have the kind of naively written code. And then you have a set of pragmas that describe how you might transform this code, or how the compiler should transform the code, in order to generate a high performance implementation of dgem. And just to show you what this particular example does, it produces code that looks like this. So obviously the code on the previous slide is more maintainable than this code. And this code, I should point out, is even itself abbreviated because there are things like runtime check and original code here, which are omitted. But obviously this code is difficult to get right by hand, and it's something that a compiler can more easily do using when provided instructions. And that set of pragmas actually produces a dgem which is not as high performance as you could possibly get, but it's actually pretty good. And much better than the default optimization level. So the default optimization level, dash 03 with architecture optimizations is on the bottom of this slide. And it takes 74 seconds, for example, to run. And if you add those pragmas, then you get an implementation that runs in 2 seconds. So there's more you could do, and that's something that is under investigation. But that's a pretty significant improvement for just being able to add some pragmas to the source code. All right, but you might say, okay, great, but how do you do better? Finding the set of transformations that you need is hard, and the search space is very large. So one thing we've been doing is we've been investigating auto-tuning for this purpose. We have auto-tuners that can explore this hierarchical space, which I'll point out is actually not trivial, because most auto-tuners, existing auto-tuners wanted a kind of fixed search space. And the space of possible loop optimizations is much too large to flatten it and express it as a fixed search space. So instead, we've been developing this Monte Carlo tree search technology that will allow us to efficiently search the space and avoid getting trapped in local minima and so on. And you can see here that as you search through the space, you will find sets of pragmas which are significantly better than the default set. And allow you to actually use this kind of technology to really tune codes for optimal performance. And in addition, though, I should say that while in some cases we can do this auto tuning, it's also the case that people, users would like compilers that have a good set of heuristics for optimizing code. And we've been developing a new loop optimization infrastructure. This is again Michael's work. In LLVM that can take loop nests that can explore the space of potential optimization plans for those loop nests by cheaply computing surrogate cost models, and then make a selection that is good, even if it's not completely optimal. And we can improve, via auto-tuning on those selections. The other thing I want to talk about is optimization of OpenMP programs. So, one thing that has long been a problem with OpenMP in the compiler is that the compiler sort of implemented the OpenMP too early in the pipeline. So, the OpenMP eventually has to turn into calls to run, to the libomp runtime library and so on. But if you do that too early in the optimization pipeline, and then the optimizer doesn't know anything about the runtime calls, then you'll actually inhibit other optimization. And in fact, there are a number of kind of well-known examples where enabling OpenMP and then running on one thread is much slower than just not enabling OpenMP and running on one thread. So of course you could say like, well, you run in parallel, and so it's faster in the end, and that's true. but it's still much slower than it could have been because you pay that serial, degradation in every thread, right? So if the overall code, if the serial performance could have been twice as good, then your parallel performance could have been twice as good. Now, it may not necessarily be true because of resource limitations, but you get the idea. There's a significant issue if you turn on OpenMP and that makes the serial performance go down. And this is something that we wanted to look at. And part of this is an optimization issue because the runtime calls hide the semantics of the program. And so we have two things that we're working on. So one is that we are integrating user feedback into the program, which provides the user with a better idea of how the compiler is actually optimizing or not optimizing OpenMP. This is particularly important for offloading because in offloading, there are various choices the compiler has to make about how to offload, and some of these have better performance than others. And also, we have an infrastructure in LLVM to actually optimize around OpenMP constructs to kind of claw back that performance degradation that we saw a couple of slides ago and make it so that the serial performance of OpenMP code is comparable with the serial performance of non-OpenMP code. And thus, we don't really have the same kind of overhead. All right. Lastly, I just want to point out that there has been work across the ECP with LLVM. One place where work has been done is on, as part of the Proxy App project, we have incorporated into LLVM's test suite a number of DOE proxy apps and ECP proxy apps. And these are used now by the entire community to help track the performance of the compiler and make sure that we don't degrade the performance of our use cases. And so with that, I'd like to thank ECP and Oscar and the Oscar facilities for supporting the work and their entire LLVM community. And I suppose I have a few minutes for questions. Let's see if I can see.
Thank you, Hal. If there are some questions.
Yeah, let me see if I can get to the chat here. Where's the chat? Chat, here we go. Okay. Where
there may be some more during the course. If you can please monitor the chat for a few minutes.
Okay, good. Yep. If anyone has any questions, I can.
Yes. Thank you very much.
Talk them or speak up.